My name is Mina Botros. I'm Egyptian by birth, and I'm a master's student here at the SDM program. I'm in my second year. I've accumulated over 7 years of professional experience working in oil and gas and technology consulting. I started out my career as an optimist. I thought organizations were well-oiled, perfect machines, but I was very quick to realize that that's not always the case. So that's why I applied to the SDM program, and that's why I'm here today. Our next speaker is one of the individuals here at MIT who has helped me look at organizations through a different, more critical lens. Dr. Brian Moser is a lecturer in the SDM program here at MIT, which is focused on engineering and project methods to solve complex socio-technical challenges. Since 2013, Brian worked with other core faculty, and they led an innovative integration of systems engineering, system architecture, and project management courses. Dr. Moser is also faculty at the University of Tokyo, and he obtained his doctorate degree from the Graduate School of Frontier Sciences. In addition, he's the director of the Global Teamwork Lab over there. Brian is also founder and CEO of Global Project Design, and since 1999, GPD has helped companies work through performance for systems teamwork using Teamport, which is a proprietary software using model-based project design. Prior to GPD, Brian spent about 10 years with United Technologies. He led their technology development partnerships and in Asia, working with industries, universities, and national programs. And in the late 1980s, Brian was one of the first foreign engineers at Nissan in Japan. Brian has a bachelor's degree in computer science and a master's from the Technology and Policy program here at MIT. While at MIT, he received the Carl Taylor Compton Award, Hugh Hampton Young Fellowship, and Alumni Award for Excellence in Technology and Policy. He develops courses and gives lectures all around the world, including as adjunct faculty at the University of Virginia Tech, University of Denver, and KU University. Dr. Moser believes strongly in the role of engineers and scientists in public life. He served as president of the student body here at MIT for 2 years, and as such, he became the first person ever in the history of MIT to serve for 2 terms. And with that, please join me in welcoming Dr. Brian Moser.
Thank you, Mina. It's always interesting to be reminded how old we are. It's so good to see so many friends and also some new folks. And today I'd like to spend about an hour with you in conversation to share some new research that we're spinning up that I think extends the work in projects as socio-technical systems we've been doing already, but leverages some of the thinking in the talks you've already heard today. If my colleague, Professor Devek, is interested in systems of systems, and I've heard a lot of good comment on your complexity lecture this morning, my main interest has been on teams of teams working on systems of systems. So we'll talk a bit about that. So I'll start to begin with just a little context. Given my role here in teaching project management, what do we mean by project management? And what is it about the conventional ways or classic ways of framing engineering projects that gets us in trouble? I'll try to define a way of framing and doing research on engineering projects that we're excited about here. And I'll try to conclude with a summary of that research strategy. And of course, as I go, I hope you provide feedback, commentary. Don't wait to the end. If you feel free to jump in. So, as was mentioned, we've worked very hard the last 4 years to rethink about the core curriculum so that system architecture, system engineering, and program management are not separate topics, but they're integrated. And we're not done yet. We're still learning. For those who are currently going through the core, you can attest to what a 68 lecture, 68 recitation, 21 assignment, and 4-month team project mean. It's a demanding load, and it's intentionally so. For me, for program management, our top learning objective is shown, but the key is to understand the project as a system itself that is part of our design choices, both architecturally and in how we implement for high performance engineering results. And that is that we're doing project management as a strategic characteristic of the project, not simply as an accounting or management exercise alone. So the high-level framework, of course, for project management that we use is common to most companies, but we think about the existing exogenous, the environment of a project as it's being shaped, often over years or months. And there's corporate standards, and there's existing resources, and there's conventional wisdom and tribal knowledge that are all in that environment. And we prepare, and hopefully, based on some decent basis, hopefully there are targets well understood, both technical targets, but also business and social targets as well. So we plan, we perform, and we deliver. That's simple, right? Well, of course not. And so we begin thinking about these engineering programs as systems. We have to recognize that we are monitoring and adapting as we go, which leads to eventual delivery of some sort. And we're trying to constantly trade off between doing the right job and doing the job right as we go. So that's just a general framework or context. The key here is that we are pulled in the iron triangle towards delivering an engineering system that, of course, meets whatever the market-facing targets are for stakeholders, but within a real-world limited environment, limited in schedule, limited in cost, and with scope trade-offs as we go. So where do these classic methods come from? I think for those of you who have been in the class or who maybe came 2 years ago when I talked, I always ask this question. So what year was the Gantt chart? So the first publication I found is 1903. 1903. And the way of, and it's not that the Gantt chart, I mean, we use Gantt charts, of course we do. It's a nice way of expressing what a project is, but it's a model. It's a model that shows us how those who created it think about what a project is. So if we go back to those origins of the Gantt chart, back to, in this case, 1911, the first conference of scientific management, which was at the Tuck School, and Taylor and Gantt and all that whole gang was there. There's a few deeply embedded assumptions about what is work and how to organize it that often carry forward today. The first is that it should be planned completely ahead of time before a single move is made. And the secondly, that is done separately by wise scientific managers who can then control the program centrally. Now, of course, in the way our enterprises work and whether we're using other techniques, we know that we don't do it this way anymore. But there's some deeply embedded, these deeply embedded assumptions often come back to bite us, and we'll talk a little bit more about that. We also are influenced in our classic way of thinking about projects, engineering projects, by the whole set of different standards. Is anyone here a member or certified by any of these organizations on the list? You may know PMI, the Project Management Institute, and their certification for PMPs, but there are many more besides that as well. Oh, their list isn't there yet, so sorry, trick question. So PMI here in the States came originally predominantly out of construction and manufacturing. Prince 2, which came out of the UK and more prevalent in Europe. IPMA, which more Eastern Europe at the time, more capability based, and so on. And then Japan has its own. You can keep going. And if we look at these kind of standards, these ways of expressing and organizing what projects are, we can also see in INCOSE and other organizations how we do systems a similar pattern. And this is good stuff, though, right? It's some very wise people got together and looked at what a good framework might be for how we do engineering projects and how we do systems. But I'm going to argue today that that is no longer sufficient, because the nature of our work and the nature of our organizations has changed dramatically, tied back to what Ollie presented this morning in terms of the inherent nature of complexity today compared to what we could rely upon even 30, 40 years ago. Not quite ancient history, but recent. So there's two projects that I'm personally involved in that I want to share with because I think they both show us a little bit about why this is an issue. On the left was a leading manufacturer of industrial machinery, had a project that had a significant market share, high margin project, so very important to the business. They had, because of the importance of the project, had doubled or tripled down on project management standards, project management practices, and project management tools. They had an 8-person team develop a 60,000-line Gantt chart. It was, from the point of view of a project manager, it was a thing of beauty, filled up a room, and people were very, very busy trying to maintain this. Has anyone seen a Gantt chart this large? You have, so Susan. Right? So what happens when this becomes, when we, I'll say, double down on this, what I think is a classic view of what work is and how we manage it? When we talk to, of course, the executives and the team leaders who are on a daily, weekly basis trying to understand the forest for the trees and make decisions and adjustments, they had very little awareness of the whole program. In fact, this approach did really just the opposite of what it was intended to do. It muted their ability to make better decisions. It muted their ability to understand what their alternatives and options might be. And over time, the chart and reality continued to diverge. Was that fair? Susan, yes, shaking her head. Good. Another, I know we have some NASA folks here today, another program, a Space Flight Systems program. And if we look at this program, it was, from a project management point of view, it did everything we would traditionally train a project manager to do in terms of the way the program was characterized, the project management documents, and so forth. And also from a system engineering point of view. The requirements were well described. They were decomposed. There was a mapping of requirements to scope. Work packages and their interfaces were clearly defined. So all the things that we teach traditionally were done. But if you look at outcomes, I think we can claim that the program itself was not necessarily a success. But there's one quote I wanted to bring to the table because I think it expresses what we're trying to get at least what I'm trying to get at today. One of the chief system engineers said to me, we were talking about the program soon after it was canceled, kind of what happened? Why is it that when we did all the things we were supposed to do, our performance didn't follow? Because we were promised that if we did all this with great rigor, the performance would follow. And she said to me, Brian, what's remarkable is that when it got to people doing their own work, they had no feeling for the dependencies. Their awareness, their ability to learn, to unlearn, wasn't, in fact, maximized. And so people followed in the traditional way. So I want us to be thinking about that. And because of this, we want to try to understand projects, at least engineering projects, not as processes, but as socio-technical systems. So what do I mean by that? Well, I think the fundamental trend here is to go from practices to dynamics. If we look at the classic project management or the frameworks, if you've been to a bookstore lately, they still exist. If you go into Amazon and you look into management self-help, right? How many frameworks are there? How many top 5, top 9 lists are there for what it is to be a good manager? It's almost endless, right? And it's not that these don't have a basis. They do. Some very thoughtful, wise people put together these frameworks. But like in PMI's project management body of knowledge, these evolved over decades. And they responded to experience and know-how from what in the past was a more stable environment. But the underlying dynamics, the underlying reason that these frameworks made sense for the context they were in is often hidden or missing. So this is what we have to keep in mind, is that our organizations and their behavior might evolve at a different pace than the environment in which we're asking them to work. And because of that, the standards we have, the practices we have, may not keep up. So what's a system? Parts, relationships, elements, topologies, architecture, beyond peer-to-peer relationships. So we know kind of what a system is. So what's a project system? So the key in a project system, when we think about it, is that it's a socio-technical system. The choices we have on how to organize our work are both technical and socially, not purely social. There's some things about my project that are a given, technically. How much complexity is embodied in the requirements and the capabilities we have at hand. Some of the teams we're working with are known and given. We can't change them. We can't train everybody. So these two things we get to think about. On the socio side, that project teams exist in organizations that have values, behavior, skills, structures, priorities, capacities, and so on. Technically also matters. I can't take a generic project framework and approach and apply it blindly to a technical system that itself has its unique topology, has complexities in places that are different than the last time we did a project. I can use those standards to help reduce some ambiguity and to maybe get along, but I can't apply it blindly. So we think about these social elements and technical elements as a system, and they're tied together by roles and responsibilities, by dependencies. I can make a technical change which shifts this. I can make a project assignment change that changes it. And most importantly, people in this system have behavior. How many of you have been in an organization where you've rolled out process workflow, standard work, you have people with a lot of Visio charts on the wall, and you have some IT system that's trying to help people along in that process, right? So for what kind of work does that make sense? There are kinds of work where that maybe is assistive. But at least in my personal experience with a lot of companies in the last 5 years, in many cases it has not been effective, right? It's missing the fact that people have behaviors. So let's go into that a little bit more. Humans here in this project as a system are in the loop. They're part of the system. And so, you know, people do work, we know that. So when I log into my process workflow system and it says, here's the 5 things you have to do, and I can do them and check them off, that's my work. I can do my own work. But that's not all that we do. We process information. We interact, I hope. An interaction in engineering systems of complexity is critical. Which dependencies? Are we budgeting for the interaction? Do we know where the interaction is of value? Do we know interaction is not of value? Let me say that again. Do we know where interaction is not of value? Having everybody in the company have access to everything, is that helpful? No. Do you ever go to a meeting that's not valuable? Does it take time? Does it take budget? Okay. So people do work, they process information, they interact as part of an organization, and then individuals in that role allocate attention based on their behaviors, their history. They may be very well intended, they may be not well intended, but they are choosing amongst multiple things that they can do today based on this pattern of allocation of attention, and it's within limited capacity. And they make mistakes, right? And hopefully they learn. So this is a more natural way to begin understanding the cards on the table when we're heading into an engineering project. It isn't just not only our choices about what technically we will pursue, but what are the resources and how they're organized as we put them together. And we call this the design of the project. Because when we put this together, the project organization then exhibits emergent behavior. So the cost, the schedule, and the quality of our new system is an output, not an input to this approach. So we want to then pursue new methods and tools for systems thinking that aren't simply a regurgitation of frameworks based on conventional wisdom and past work, but that actually allow one to examine how the situation at hand might lead to worse or better outcomes. We want to design our engineering projects, not simply manage them. So we need an integrated view of these projects that have the product point of view, a process point of view, and an organizational point of view, often not in balance, if you look at what people use in most companies. We want to be able to forecast the surprising, likely, and emergent outcomes. We have to have a system that gives us answers we don't want to see, right? You know, I don't know about your organizations, and I know about a couple of your organizations maybe. But if you step back and look at kind of the weekly project reporting and the red, yellow, and green things that go around and the information that flows up to the top and the dashboards and all the rest, it's very likely that we don't permit unexpected answers. It's a way of managing the projects that don't permit us to see an answer that we don't want to hear. And it's very important for us to overcome that. The last thing I'll say, and this goes back, I think, to the previous discussion about what's the role of augmented intelligence or other AIs. These approaches allow the participants to search the trade space, to actively be part of the search. Not an automated workflow, not a black box that spits out a project schedule and work and people just do their work. It really just goes back to kindergarten, to Montessori. The time spent socially as part of the planning, as a part of understanding the project, building the awareness of what the project as system is very, very important. So this exploration of the trade spaces I'll show you is important, takes time, and therefore the design of the project is a social instrument. And I will argue that is necessary for high performance on complex engineering programs. If there is no complexity, or the complexity is pocketed properly, then maybe you don't have to do this. Think of it this way. If you're a factory in 1910, 1915, where resources are replaceable, where all dependencies are sequenced, where all tasks are fixed duration, and you can control, reduce variation, if that's how you think about your engineering projects, and that is your reality, then you don't have to think of it this way. Okay, so that's kind of how I think about this. And so let me describe some to me exciting, maybe not to you, but to me exciting research mechanisms that we're putting in place to kind of unfold this problem a little bit more deeply. I'm lucky to be part of a wonderful group and a new campus at University of Tokyo. Has anyone been to University of Tokyo here? Well, some of my friends have. I brought them there. And this campus is now about 5 years old. It's part of a smart city. The entire campus is graduate level research, multidisciplinary, focused on complex socio-technical challenges. We have over 200 faculty. We have hundreds of doctoral candidates. We have 1,400 master's students. And it's part of this city that the city itself is instrumented. It's a huge experiment. So if you're interested to come visit this smart city in Kashiwa in Japan, please let me know. Happy to show you around. But in this new campus, as part of our school, we've now established the Global Teamwork Lab. And the purpose of GTL is to explore and predominantly to run experiments to understand engineering and other complex problem solving as a system. So the teams themselves, but not just the teams, but the problems they're working on simultaneously in their environment are instrumented. We want to observe what's happening in the socio-technical system in real time. A friend of mine who works at BP, we were talking about Deepwater Horizon and other kind of aspects, and he was saying to me, Brian, we spent so much money on the robotics and the sensors and the instrumentation. We knew the pressures and temperatures. We knew all these things. We didn't know what the people were doing necessarily. We don't have an equal investment and attention into all the things that happen. And I know in construction projects and other capital-intensive projects, where people are and what they're doing and the choices they're making are often the determinant of what's later a safety issue or something else. So we have to think about instrumenting the problem, the technology, and the people simultaneously and connect them together. And of course, we do in this laboratory, we do modeling and simulation to be predictive, but we want to balance that with empirical work, with experiments. So let me try to introduce this to you a little bit. At the heart of it is workshop-based experiments. We have a lot of assumptions now from all these frameworks and from decades of interesting social science research on what teamwork is. First, we want to be able to understand the physics. We have a lot of, from the existing standards and best practices, can we explain why they make sense? What's the underlying reason that they're proposed? And we ask each of our participants to design an experiment to observe teamwork, physics we call it, in real time. This is, the workshop environment itself is, and often these are industrial class workshops where a team of teams is gathering, maybe not even co-located. And to the participants, they're fluidly working in that environment on a real problem, whether it's designing a new engineering project or working on ideation for new architecture and so forth. But at the same time, we're creating that environment so that we can do research on that highly instrumented environment at the same time that they are actually doing work. So as you've heard from me, my point of view is that planning is actually designing, that we should design our projects. And any project for its plan there's a lot of ilities, as Professor DeVeck will tell us. But at the heart of it, I think, is a choice between feasibility and desirability. I mean, we poor program managers, at the end of the day, are left with a real schedule and a real budget that have real limits that cause choices. So this tension between what's feasible and desirable, the sooner we get ahead of the curve and design our program or adjust our program, the better if we are. So that's how I think about it. Project planning is design. And so in an engineering project, there may be targets, but how many plans are typically explored? How many project plan alternatives are typically explored for major engineering projects before they're approved?
A handful.
One, maybe. It may be asserted. It may not be designed. So what I would love for, if you're an executive, to ask the question, you just brought me a project plan that says you can deliver this by October 10th. How many project plans alternatives were investigated? Did you design this plan? Where does it come from? Okay? So we think of this in a trade space. In this case, what I'm going to show you is cost and schedule. We can also look, of course, at scope and quality and risk. But if I look at duration on the x-axis and cost on the y-axis, and I have some baseline initial plan that may come from standard work, I may have some sort of calculator that shows me what this kind of project should cost or should take, right? That's a starting point. And it may reflect kind of all the default assumptions from purchasing, from engineering, from manufacturing, okay? The question is, if I design, and I have, this is utopia down here, less duration, less cost, without trading off quality, I'm going to make a change in my project somehow. I'm going to change how we organize the workers. I can change how I organize the work. I can look at increasing concurrency. I can change, there's a lot of things I can change, both on the social and technical side for alignment. And when I make that change, what's important socially is that the team of teams is involved in that discussion. There's some reason why they're thinking about this alternative, because their behaviors will have to change in order for this to be real. And so that one vector here is a new design for the project. So every time I look at this, I'm developing or uncovering the trade space for the project. So here's an example from class. Have anyone been in this experiment before? Maybe a few people here? This is the City Car project, which was a project done here on campus at the Media Lab. And we've taken the product, the workflow, and teaming from this project and developed a project model. And what you see here in red are aspects of the product breakdown structure. In blue across the middle, you see aspects of phasing or work breakdown structure process, but also teaming. So even these three breakdown structures By changing the breakdown structure, you will change the likely cost, schedule, and quality of this program. That's the design problem. So we gave the participants this common starting point, and I think in this case 2 hours, and we said, how many project plan alternatives can you generate? Now here's the key. We're teaching them about project management. You know, the exercise itself has a pedagogic purpose about what really happens to a schedule when you have resource limitations, sharing resources. Where is it the concurrency helps? Where does it hurt? So that's the pedagogic point of the exercise. But we're also watching and observing what's happening while they're doing it. So let me show you. I think this is supposed to. This is the original baseline plan, starting point, common to 20-some teams in this case, is here. That is a little bit over $10 million, so a pretty small program, and about 2.25 years long. So that's a common starting point. I think I can, if I click here, show you. There we go. So each vector here is a design decision. Something changed about their project that they're trying to do to improve the program. Some teams, it's really fascinating. Some teams get stuck, we might call local minimum, but they start arguing ideologically about what might be better. They only end up exploring 2 or 3 alternatives. Some have a very steady strategy or progress. Others go way off and come back. The point is, that each of these, in this case, each of these points is a project plan. They're all viable project plans. They're alternatives in the trade space. The trade space is being covered and explored. They came back to the origin.
What does movement of a single arrow represent?
So a single arrow of a single color is one team, and it's their pathway through the exploration. So it's showing how it's path dependence in the exploration of the trade space. And so what we're beginning to want to see in real time is what led to certain teams to have more inherently robust or better answers in the end. Is their path dependence. And not only can we see where they wound up, but more importantly, we can see what were they talking about, thinking about, and what did they attempt to change as they went through the process. Let me go on. I'll give you some more examples, but I think you get the idea. This is the 2-hour exercise for this project. They developed 316 different project plans and did a bunch of simulations. So each dot is a different project plan in the trade space. All of these are viable. They aren't necessarily desirable. And in some cases, you can begin to see a frontier. I think you can. Here we go. Begin to see frontiers, but the frontier in terms of cost and schedule might not be the solution that they want to promote, because they're also trading off scope, risk, and some other issues. Move past that. And then, of course, this is the 16 teams or so for this particular exercise. Their patterns are quite different. So we're beginning to really understand, and we want to see in real time, what is it about the nature of their pathway through the trade space, but also the nature of the things they're paying attention to that might lead to a better and more robust answer. And at the end of the day, we ask each of the teams to select amongst the often 20 or 30 alternatives they were examining to actually suggest a revised project plan. And we're trying to think about, well, what led certain teams to be more cost-centric, more duration-centric, and so forth. All right. Let me give you another example of this work to understand what's happening when these teams of teams are working on projects of projects. Our colleague, Professor Horii at Tokyo, runs the iSchool, Eyes for Innovation. And he is interested in knowledge structuring. He works much more on the front end during concept generation and early architectural selection of major projects. And also his environment is highly instrumented. And he's done more than 50 of these workshops now. And so at the heart of it early on by these teams, they're using what looks like sticky notes here. I guess we can't say sticky, it's probably licensed. So colored adhesive papers. And And what's interesting is that what they're really paying attention to is in the knowledge structuring and selection process, what are the teams talking about? How is it that certain teams end up generating more alternatives, others don't, and so forth. And so this is also gives you a sense, I think it's moving here. What's important about this is a team that could be in several locations, but they're working on concept alternatives, they're doing grouping, they're selecting more prominent concepts for consideration. This entire flow is now recorded. So we can go back, and not only can we, but the teams themselves go back and kind of see the traceability of the origin of an idea, how it evolved, how it changed because of comparison to other ideas, and where that led them to in the end. And so Professor Horty has several students working on quite interesting work across these now more than 50 workshops at the different mechanisms for stimulating better ideation, to stimulate evaluation, pruning down of concepts, but at the right time, and also trying to see where certain teams develop what he calls a creative leap. And from that, there's a lot of different mechanisms that they develop, and for a control group, they'll apply only a certain portion of these mechanisms, and other groups may follow these mechanisms in order to try to get faster innovation and better innovation as well. Okay? So as an example, this is a small example, but this is actually showing that this team, as they're going across time, the participants in this sub-team here are working on source retrieval and establishing boundaries in the domain. And so these different aspects of knowledge structuring and innovation before they led to a creative leap. And this group here was working on I think, a selection much sooner. So I won't claim what the conclusion is here. I wanted to give you a sense of what we now can begin looking at and examining in real time when your engineering teams are working upstream in the case of ideation, and also downstream in terms of engineering planning and progress. Another example. I mentioned before that when someone's doing project design and they make a change and there's a vector, and that actually corresponds to a whole discussion. Why is it that you think that this particular part, it's viable, feasible, and makes sense to bring to a supplier, a different supplier? Right? And there's a lot of important context and background just to that one vector. In this case, this is what he calls the happiness counter. So they have this 360-degree camera on the workshop tables as the design teams are doing their work. And they now have analytics. They're basically counting the smiles and the frowns. And I'm sure there's a cultural element to this algorithm. But again, it gives us a way to kind of look back at that traceable history of the exploration of, in his case, the ideation space, in my case, the project design space, and try to understand what's happening in the team and under what conditions do teams actually perform better, both in innovation and in engineering planning. So one last, yes, sir? Sure, yeah, of course.
In that part of the exercise where you're measuring ideation processes, do you
Yes.
apply any conceptual constraints to represent organizational culture? Put them in this kind of culture, put them in that kind of culture. Like, why do they end up being cross-sectional? That might be an aspect of the culture of the company. Do you apply any of those?
So that's a very good question. And the question, if you couldn't hear it, is do we apply any, I think, either starting conditions or constraints which would reflect a certain corporate or team culture, and to see if that has, what the efficacy is, or what the impact is. I'd say two things. One is at the mechanisms level, we think that kind of in some sense, the DNA of teamwork, that we're searching for mechanisms that are, in that sense, culture neutral. So in the case of, certainly for the style of collaborative communication in Japan, which we're used to and the way we're trained, the students are trained for from a very early age, when we put that particular exercise mechanism on the table as an option, they are more likely to select it and to be comfortable at operating that mechanism. But I would say that I think of the culture as the emergent characteristic of how these mechanisms are actually selected, chosen, and applied. Here's another experiment. Some of you may remember my lecture on dependencies, I think it was 2 or 3 years ago. But we've continued this work to understand not just what is a dependency in engineering. So going back to that 1903 Gantt chart, Gantt charts, by the way, didn't have dependencies on them. But they've been thrown in the last 20 or 30 years. So Mike, I know we've talked about this, but so that classic view of what is a dependence in that classic project management, what is it? What does it mean?
Well, one thing needs to be done in order to.
So it's mathematically speaking, the classic view of a dependence is simply sequence, right? And that's also a deeply held kind of assumption or view. And we've gone kind of well past that on the project management side to think about dependence more deeply. But the key thing about managing dependence or coordination is that often the driver, the original reason for that sequence or that way of framing the problem is forgotten. So we want to try to maintain linkage and connection to the sources of need, and there's different kinds of needs. But there's another part of the question. What does it mean to satisfy dependency? How do we know in a project that the dependencies have been satisfied? That it is okay at this point for the teams working perhaps in parallel to proceed as if they are independent? Can you trust the interface? Do we now assume that the dependence has been satisfied? Okay. And so what we realize is that in the act of building an engineering team and building high performance, it isn't simply the definition of dependence, but because people are making allocation attention in a limited capacity, their awareness of the dependence also matters. Going back to that feeling for the dependencies I mentioned. So you could have every process-driven, well-defined dependence, clear interfaces, but if people aren't aware of them, what are they going to do? They're going to proceed along in their work based on what their habits and other things show them. So what we were trying to understand is that if interaction is the response to a dependence, because if I'm not dependent, I don't need to interact, right? So if interaction, I need to understand, are people aware of which interactions are of matter and of value? And where does that awareness come from? So we are building a model that gets to the heart of not simply managing work, but managing interactions through this understanding of dependence. So for our research, that means when we are looking at an engineering project team during upfront innovation or during engineering planning, can we see if people are paying attention to or aware of dependencies? Can we see if dependencies are being satisfied? So Ali, your work will give us strong hints about systemically where interaction may have value, where uncertainty reduced is more systemic value. This work in the team of teams is about how do we organize the work so indeed people are aware, are acting upon, and their acts for coordination are actually being effective. So we have an experiment now that is actually just about underway, and we have 3 different places where the experiments can be held in the next 3 months. But we're actually taking a look at not only the design results themselves, that's the design walk I showed you, but we're taking a look at what we're calling fingerprints. We're actually paying attention to not only what people change or do in a project, but what they're looking at, what they're paying attention to over time. So if a team that is spending all their time looking at only part of the program and not paying attention, are they more likely to have a better outcome? We don't know. That's what we want to find. And so in the analysis and across these groups, if we think about all the attention and actions. I'm paying attention to this, we're arguing about whether or not we should outsource this to a supplier. At the end of the day, we paid attention to it, but we didn't do it. So sometimes we pay attention but don't do anything. Think of that as a tree or, in fact, a layered network. The question is, can we see anything from the view of those interactions and those decisions or changes over time across these different groups, given the different makeup of the group? For this experiment coming up, we're actually in the way the problem is being set up, we're actually allocating time, more time, in the exercise for some teams to pay attention to dependencies. Now, we don't know if they'll take the bait, and we don't know if they'll take the bait and that actually causes a difference in their outcomes. But for the first time, rather than just having a debate about it, we can actually run an experiment and see. And so that's what we're doing. Let me skip through that. So let me try to wind up, and then maybe we'll have more of a conversation and tell you what do I think this means in terms of a research strategy and agenda moving forward. So, I mentioned before a team of teams for system of systems. We're interested in the mesoscale in this case. 7 times 7 times 7. 300 and what is that? Something. 40 something. Right? Much research for decades exists at the microscale. Design teams, personality tests, a cognitive view of attention, right? There's a lot of new emerging work at the macro scale. That is big data applied to populations. If we do regression on large populations of large transactions, what can we see? This work is squarely centered on the mesoscale. That really probably the 40 to 400 range that is most common to what the kinds of complex engineering projects I work on, where that core team size matters. In this, we want to begin understanding tasks and their relationships more deeply. I think, Ali, this morning you were talking about kind of new rules of systems, right? New principles of systems common across different, both natural and human engineered entities. In our case, I would argue that the classic work on project management views tasks as an atom. But we want to find the subatomic particles of tasks. The quality of work, the cost of work, the duration of work is emergent from the interaction of these other things. So we're going to reveal the underlying characteristics of tasks and how they interact dynamically with their socio-technical environment. We want to do that because we want to better understand how to describe the work at hand, how to see what happens when we associate work that's demanded with certain kinds of teams, and to predict so that we can then later design. I think this is important because we have the potential to change the scale and the pace of research in this area. There's probably quite a few PhDs in this room, right? And we kind of know if you have a PhD, you know the kind of burden and pace required to do a proper experiment. I think that has a chance to change. So, even in my work as well, what it takes to do really proper and good ethnography is nothing to sneeze at. It's very important. But we can do survey-based, self-reporting, deep ethnography, and then we often set up some toy problems in a game to play with. The key here is, though, that often these insights are helpful as shadows or vectors of the way to go, but they're often not in a form that allows us to scale or repeat these experiments. To me, that's a real weakness. And you'll find, for some of the things I talked about, allocation attention, there's one classic paper from the early 70s, and then that one classic paper gets repeated for decades with slight shades of difference, okay? So I think what we want to do is, by having a platform for conducting these experiments in a way that is both scalable and repeatable, we want to do what used to require a PhD, we want at a master's level to do many more experiments, but with the proper rigor. So this is the opportunity. But still at the mesoscale. And And the key here is this premise of commonality across domains, which I think Ali mentioned also this morning. I have a lot of respect for performing artists, for sports teams, for government and military organizations, for, we humans have been doing just beautiful and amazing things for a long time. And so these high performance work cultures evolved, for a reason. So it is in that traditions of teamwork, if our research is good, then we'll be able to explain better why they evolved the way they did, why they make sense. I think as Ali mentioned, whether it's a natural system, an industrial system, an economic system, there may be things that we can learn from one and apply to the other. And in some cases, we do have choices in how we either structure, select, or prioritize and manage the work. I come back to that conversation I mentioned that I had with my colleagues at BP, which is that it's not, we shouldn't be arguing ideologically about whether we should have work, waterfall or agile. I mean, it's a religious argument. The question is, for the complex program at hand, can we actually see in real time whether or not teams are innovating, whether teams are exploring the trade space robustly, whether they're happy? And can we see predictively then, by making adjustments, how it might unfold differently? So with that, I'd like to open up for some questions. Thank you.